Hello again. I'd like to welcome you to the first of 5 lectures that we'll devote to applications of derivatives. Up to now, we've developed the rules for finding or calculating derivatives, and basically we have now the ability to calculate just about any derivative that we ever need. And in the next few lectures, we're going to apply our knowledge of derivatives to some applications. In particular, we'll look at how you find the maximum value of a function or the minimum value of a function. That function might represent profit for a company, and it would be good to maximize that function. Or you might want to minimize the amount of material you need to construct a box or something. And these problems are real-life models, and often are simplified in calculus courses because a true model of a real-life situation might indeed be much too complicated. It might take days to develop the model and then apply the calculus. We'll see simpler models as we go along in the next few lectures, but the principles we use will be the same as you would use in the real world. I'd like to start with a fairly simple example to show you where we're going today. And I'd like to consider the function x squared minus 2x defined on the closed interval 0, 4. And here's the question. Given that function, it's continuous on that interval 0, 4, can we find the absolute maximum value of that function and the absolute minimum value? What I mean by that is the following. Imagine the function between 0 and 4, it does some curves, and there'll be some high point of the graph. I want to know where that high point is. There'll also be some low point on the graph. I want to know where that low point is as well. Now, what we'll notice here is that these high points will occur when the derivative is 0, or perhaps the derivative is undefined. Or, as we'll see in this example, in fact, one of these high points or low points could occur at an endpoint. So let's do the problem. Our function is x squared minus 2x, and we're trying to find the high points, the absolute maximum value, and the absolute minimum value. So let's take a derivative, that's 2x minus 2, and let's set the derivative equal to 0, and we get that x equals 1. So at x equals 1, the graph of this polynomial has a horizontal tangent because its derivative is 0. Now, where could the maximum values occur? Well, they could occur at this point where the derivative is 0, in other words, at x equals 1, or they might occur at the endpoints, at 0 and 4. So what you do is you evaluate your function at all of these 3 candidates. These are the candidates for the absolute maximum and the absolute minimum. Well, let me evaluate them. You evaluate, by the way, back in the original function. So f of 1, if I plug it into the original function, I get minus 1. At x equals 0, the function equals 0. And at x equals 4, the function equals 8. So who's the winner? 8 seems to be the largest value. So the maximum value of this function is 8. And it occurs at x equals 4. Where's the minimum? Well, the minimum value is minus 1, and it occurs at x equals 1. Let's look at a graph of that polynomial we just analyzed. Notice that it starts at the origin and goes up to the point 4, 8. 4, 8 was the maximum of the graph, and the minimum occurred inside the interval at x equals 1. And you can see that the point 0, 0 is neither an absolute maximum nor an absolute minimum. So I've used these words absolute maximum, absolute minimum. Here's the precise definition of these terms. Suppose f is defined on an interval containing the point c. If f of c is less than or equal to f of x for all x in that interval I, then f of c is called the minimum, or if you want, the absolute minimum of the function f on that interval I. And the same for maximum values. We say that f of c is the maximum value of f on that interval I if f of c is greater than or equal to f of x for all x in that interval I. In the previous example, our interval was 0, 4, and we determined the absolute maximum and the absolute minimum using some calculus. These are often called the extrema of a function, or the extreme values. It's the top value, the winner up here, and then the lowest value. And by the way, ties can occur. We'll see some examples where there is more than one location where an absolute extrema occurs. So we'll see one a little bit later. Now, do all functions have absolute maximum and absolute minimum values? Well, if you're defined on a closed interval, and if you're continuous on that closed interval, then the answer is yes. This is called the extreme value theorem. It says the following: if a function f is continuous on a closed interval ab, then it has both a minimum and a maximum value on that interval. I think you can believe that geometrically. If I have some function that starts here, and then it's continuous, so it ends over here, it will have a high point and a low point. Because it's continuous, you don't have any breaks in the function. So it seems logical geometrically. It turns out this is a very difficult theorem to prove. You won't find the proof in any calculus textbook. It requires knowledge of the real nature of what real numbers are, and is beyond the scope of an elementary calculus course. This theorem, you notice, doesn't tell you how to find those absolute extrema. It just says that they're there. And we call this an existence theorem. In other words, it claims that they're there somewhere, but it's going to take some calculus to find them. And we'll learn how to find those absolute extrema in the next few minutes. And to do this, I'd like to talk about a different kind of maximum and minimum called relative extrema, or local extrema. Let me talk about this by showing an example first. As you probably noticed, I like to do examples before I get into the theory of calculus. Let's look at the function x cubed minus 3x squared. It starts down there at negative infinity, and it goes up, and then it comes down, and then it goes up again. And at the point 0, 0, the function seems to turn around. It has a maximum there locally. In other words, in a small interval around x equals 0, the point 0, 0 is the high point of the graph. Similarly, look at the point 2 minus 4 on the graph. That's not an absolute minimum, is it? The function goes below that value far away. But locally, around the point x equals 2, the point 2 minus 4 is the lowest point on the graph. That's what we mean by relative or local maximum values or minimum values. Locally, they're the winners, or the losers, if you want to say it. So, let me be clear about some of the ways of expressing the results about relative extrema and even absolute extrema. You have to read a calculus problem very carefully to see what they're asking. For instance, in that previous function that we looked at, the relative minimum occurred at the point 2 minus 4. There you see it. It's kind of the local low point of the graph. How do you express this? Well, what I would prefer that we say is the relative minimum value is minus 4, and it occurs at x equals 2. So read the problems carefully. Are they asking for the relative minimum value, and then the answer would be minus 4, or are they asking where does it occur? And that answer would be x equals 2. And again, I hope we're clear on that difference between absolute extrema and relative extrema. The absolute maximum is the top point all over. It's the winner on the entire function. The relative maxima are locally winners, but they might not be the global high points. Here's a technical definition of relative extrema, and it kind of reflects what I was talking about. If there's an open interval containing C on which f of C is a maximum, then f of C is called a relative maximum or a local maximum. In other words, you have to have an open interval around the point where C is where f of C is the maximum value on that little open interval. And a comparable definition, of course, for relative minimum. Okay, well, we've seen that in that previous example, that the derivative of the function at these relative maximum values and relative minimum values seems to be 0. In that graph I showed, at the point 0, 0, the function came up and then went down, and at the origin, the graph was flat. If you took the derivative of that function, you'd see that the derivative was 0 at that point. Well, this is the part of the definition of what we call critical numbers. So let me define critical numbers, and then we'll talk about them for a moment. Let f be defined at c, some value c. If the derivative at c is 0, or if f is not even differentiable at c, then we call c a critical number. So the critical numbers are the following. They're the numbers where the derivative is 0, or perhaps the derivative doesn't exist. And the point is, these are going to be our candidates for relative extrema. Where the derivative is 0 is where it has a horizontal tangent, and where the derivative does not exist might be a sharp corner, and that also could be a relative extrema. Here's a picture of a couple of these cases. On the one hand, you see a curve that has a sharp point, and that is a relative maximum. In fact, it could be an absolute maximum. It's not clear what the function does outside the part that I've drawn. But locally, that sharp corner there, that point there, a cusp we sometimes call it, is a relative maximum. And then the other picture shows a smooth curve, and the high point there satisfies the property that the derivative will be 0 there. It has a horizontal tangent there. Good. Now, there's a theorem which tells us the strategy for finding relative extrema, relative maxima, and relative minima. And this will lead to solving the problem of finding the absolute maximum and absolute minimum values. And the theorem is very simple. It says that if f has a relative minimum or a relative maximum at x equals c, then c is a critical number. So, the candidates for relative maxima and relative minima are the critical numbers. They can't occur anywhere else, just at the critical numbers. You got to be careful here. There's a little pitfall to be. You might have a whole lot of critical numbers for a function. Some of those will not be relative maxima or minima. The critical numbers are just the candidates. You might have 10 critical numbers for a function, and only a few of them are relative extrema. Let me give you a simple example of what I'm talking about. Look at the function f of x equals x cubed, whose derivative is 3x squared. Now, because the derivative is 0 at 0, we see that 0, x equals 0, is a critical number. In other words, x cubed has a horizontal tangent at the origin. But that's not a relative extrema. Remember the graph of x cubed? Here's that graph. You see that at the origin, that point is not a relative minimum nor a relative maximum. The function motors up to the origin, and then it keeps going up, doesn't it? That's not a relative extrema. Now, the theorem I just talked about, the fact that relative extrema occur at critical numbers was first, well, mathematicians think in the history, it's not too clear, but they sometimes think that Pierre de Fermat, who lived in the 1600s, was the person who first used this theorem. He's a very interesting character in the history of mathematics. He was trained as a lawyer, and for him, math was just a hobby. And he developed many of the fundamental ideas of calculus before Isaac Newton and Gottfried Leibniz actually came along and put calculus together into a package. If you go on and take other mathematics courses or read more about mathematics, you'll see the name Fermat just about everywhere. He has results in all areas of mathematics. One very interesting area is number theory, and maybe you've heard of the theorem called Fermat's last theorem. Let me pause here and tell you very quickly about this theorem. You remember the Pythagorean theorem, x squared plus y squared equals z squared, is satisfied by right triangles, x and y being the legs and z being the hypotenuse, like a 3, 4, 5 right triangle. 3 squared plus 4 squared equals 5 squared. Well, Fermat said, suppose you change the squared, the 2 exponent, to a 3, or a 4, or a 5, or any integer. Are there solutions to that equation? In other words, x cubed plus y cubed equals z cubed. Are there any solutions in the positive integers? And he claimed, no, there aren't any. And it wasn't until very recently that mathematicians were able to prove this theorem. It occupied mathematics for hundreds of years, and a lot of the greatest mathematicians worked on Fermat's last theorem, and only recently was it proved to be correct. There are no solutions, except for the case when n is 2. Okay, back to our calculus. Let's do an example that puts all these ideas together. I think you'll see how it all comes together now with a specific example. Let's consider the function 2x minus 3x to the 2/3 power. Now that function's continuous. It doesn't have any problems. In other words, you can take the cube root of any real number and then square it. So the 3x to the 2/3 is not a problem. And I want to find the maximum and minimum values of this function on the closed interval minus 1, 3. According to the extreme value theorem, they exist. This is a continuous function on a closed interval. The question is, how do we find them? Well, here's our strategy. We're going to look in the open interval, minus 1, 3, and find all the critical numbers, meaning find all the numbers where the derivative is 0 or the derivative doesn't exist. And then we'll check the endpoints, because the extreme value could possibly occur at an endpoint. So here we go. The function was 2x minus 3x to the 2/3. We take its derivative, and we know how to do that because we have all the formulas. The derivative is 2 minus 2x to the minus 1/3. Did you see how I got that? It's x to the 2/3, so the 2/3 comes down in front, and the 3's cancel, so you're left with 2x, and then 2/3 minus 1 is the new exponent, and that's the same as x to the minus 1/3. Now I want to set that equal to 0, and it's kind of awkward the way it's written, so I'm going to do some algebra massaging here so I can handle this better. First I'm going to factor the 2 out as a common factor of the two terms, and then I'm also going to write x to the minus 1/3 as 1 over x to the 1/3. So I have a new expression now, still a little bit awkward, so I'm going to get a common denominator. And now it's 2 times the quantity, x to the 1/3 minus 1, all divided by x to the 1/3. Note the difficult pre-calculus here. Please take some time to kind of savor those steps I just did. It's a lot of manipulations of exponents. But now I have a full picture of the function's derivative, and I can find its critical numbers. First of all, the derivative is 0 if that numerator is 0, and that occurs when x is 1. Good, that's one of the critical numbers, 1. But now look at the denominator. If x is 0, the derivative does not exist, does it? So that's also a critical number. The function is continuous at 0, but not differentiable at 0, and those points are critical numbers. Great. So we have two critical numbers, 1 and 0, and then we have our two endpoints, -1 and 3. So we have 4 possible winners here. We have 4 candidates to consider. One of them or more will be the absolute maximum, and one will be the absolute minimum. So all you have to do is go back to the original function and plug in these 4 numbers. For example, f of 1 is -1. F of 0 is 0. F of -1, if you plug that into the equation, turns out to be -5. F of 3 is a little awkward because you have to take 3 to the 2/3 power. That requires a calculator. And you get that f of 3 is approximately -0.24. Trust me on that. So here are the 4 candidates. We've evaluated them back in the original function. Where's the absolute maximum? 0 is the maximum value, and it occurs at x equals 0. Where's the absolute minimum? Well, the minimum value is -5, and it occurs at x equals -1. Now, as I said earlier, this is a pretty simple example to find the maximum and the minimum. In real-life models, the functions would be much more complicated. But the principles that I just used here of analyzing the critical numbers and the endpoints would be exactly the same. Let's look at a picture of this function to verify that what we did analytically makes sense. Notice in this graph, the function's defined on the interval -1 to 3, and we have the absolute maximum occurring at 0, 0. And remember, that was an interesting point. That x equals 0 was a point where the function did not have a derivative. And in the graph, you can see that it has kind of a sharp corner there, a cusp. It's not smooth at the origin, is it? It's a sharp corner. It does not have a tangent line there. On the other hand, at the point 1 minus 1, the function is smooth. It has a horizontal tangent there. But 1 minus 1 is not an absolute minimum, but it's a relative minimum, isn't it? Locally, it's a minimum, but it's not the absolute minimum. The absolute minimum occurs over there at x equals -1. Okay, so the picture, I think, reflects our work. We have one of the extrema at an endpoint, and the other extrema occurred inside the open interval. Here are some guidelines for finding extrema on a closed interval. It's basically what I just did. In other words, consider a continuous function on a closed interval. You find the critical numbers in the open interval. You evaluate the function at those critical numbers and at the endpoints. Then you select the winner and the loser, the largest value and the smallest value. Here's a common pitfall that I see. Please remember that critical numbers must be in the domain of the function. I see people a lot doing the following. You'll have a function like 1 over x, whose derivative is -1 over x squared. And then I'll ask, what are the critical numbers? And you might think, well, it doesn't have a derivative at x equals 0, because -1 over 0 squared is not defined. Zero's not in the domain of this function, is it? It's not there. And hence, it's not a critical number. Critical numbers must be in the domain of your function. In fact, the function 1 over x does not even have a maximum value, say, on the closed interval -2 to 2. Why not? The function's not continuous there. It's not defined at 0. Here's a graph of that function. On the interval -2 to 2, the function is not continuous because it goes off to +infinity and down to -infinity. Great. Let's do a kind of a more complicated example, and I might skip a few steps here, but it has a good trig component to it that I'd like to point out. Let's consider the function 2 sine x minus cosine 2x on the interval 0 to pi. Let's find the absolute maximum and minimum values. We know they exist because it's a continuous function on a closed interval. So we take the derivative, 2 cosine x plus 2 sine 2x. Notice I'm using the chain rule for that second derivative. And I can divide by 2, so I have the equation cosine x plus sine 2x equals 0. And I have to solve that. Uh-oh, not so easy. But let me point out another trig identity that we'll use a lot. You can replace sine 2x with 2 sine x cosine x. That's another trig identity that we need to memorize. Sine 2x is 2 sine x cosine x. A few lectures ago, we saw a similar identity for cosine 2x. Well, now we have one for sine 2x. Of course, all these identities are in our workbook. So now, by that replacement, I can factor out the common term cosine x, and that gives us cosine x times the quantity 1 plus 2 sine x, and that equals 0. The product of two terms equals 0. One of them must be 0. If cosine x is 0, then you know that x is pi over 2 or 3 pi over 2. And if sine x is equal to minus 1/2, that's the solution to 1 plus 2 sine x. If sine x is equal to minus 1/2, you get 7 pi over 6 and 11 pi over 6. So, how many candidates do we have here? Ouch! We've got 4 critical numbers, and then we've got the 2 endpoints. Wow, we've got 6 possible candidates to look at. So you make a giant chart. You write down the 6 candidates, and you evaluate the function at each one of these candidates. This will take you about 2 hours. Well, not that long, but it's not, you can't do it very quickly. Let me show you the first one. F of pi over 2 would be 2 times sine of pi over 2 minus cosine 2 times pi over 2. Sine of pi over 2 is 1, so that's 2 for the first term. Cosine pi is minus 1, so minus a minus 1 is 1. 2 plus 1 is 3. And here are the other values. Minus 1, minus 3 halves, minus 3 halves, minus 1, and minus 1. I've evaluated the function at the 4 critical numbers and at the 2 endpoints. It took me a long time. But now that I have this chart, I know where the absolute maximum and minimum occur. The maximum value is 3. It occurs at pi over 2. The minimum value is minus 3 halves, and it occurs twice. Here's one of these ties. At 2 different points, 7 pi over 6 and 11 pi over 6, we achieve the minimum value of minus 3 halves. So again, this was a tough problem. It had some trig identities and a lot of trig evaluations. I invite you to check this with a calculator. Your graphing calculator should show a picture pretty much like I'm showing here. The maximum value you can see there when x is pi over 2, and you see the 2 minimum values over there on the right, where the function is the lowest. Good. So we're pretty much now, I think, comfortable with how to find maximum values and minimum values of functions. For finding these values on closed intervals, the technique is fairly straightforward. You find the critical numbers on the open interval, and then you evaluate your function at those critical numbers and at the 2 endpoints. And remember, a critical number can either be a number where the derivative is 0, that means you have a horizontal tangent, or where the derivative does not exist. And more important, these critical numbers have to be in the domain of the function. So next time, we're going to continue our study of the nature of graphs, of what graphs look like, and with the goal, again, of trying to find maximum and minimum values. We're going to talk about the following. Where is a graph increasing? A graph that's going upwards, or where is it going downwards, decreasing? And you might sort of think, well, yeah, if it's going up, the derivative is positive there, and if it's going down, the derivative is negative. So that will be kind of one of the topics for next time. So thank you very much. I hope you enjoyed the lecture, and I'll see you next time.